Yes, it seems that everyone is in. So welcome, everybody. Hereby, I open this academic ceremony in which Yiyong Gou will defend the academic thesis, Aerial Robotic Operations, Multi-Environment Cooperative Inspection and Construction Crack Autonomous Repair. May I invite you to present a summary of your study and the conclusions of your thesis.
Okay, thanks. Wait a moment. Okay, thanks, dear Prorector, committee members, colleagues, friends, and families. Thanks for your attendance. I'm really happy that you can be here. My thesis is mainly about using two different sized air robots to cooperatively inspect a small dark hole and use a reconfigured air robots to repair construction crack to prove the conception of post-disaster rescue and repair using air robots. Why do I do this research about aerial robotic operations? There is a short background of my hometown natural disaster. In Wenchuan earthquake 2008, this earthquake caused a lot of people dead and building damaged or fully destroyed. 70,923 persons are missing. This means if we can find the missing person in a quick way, the number will be decreased. Normally, after this kind of disaster, people will try to reach the disaster position or conduct a rescue, such as manual checking, use a knife detector. But in this case, the post-disaster environment is quite complex. It's really difficult for humans to enter a small-sized environment to conduct a rescue, or it's quite dangerous for rescue staff to enter this kind of environment because the secondary disaster probably happens and it will cause more serious damage or life loss. Moreover, after disaster, some important infrastructure is probably damaged slightly just in order to avoid more serious damage or secondary disaster. The repair work is important to save lives and reduce the economy loss. But repairing may be difficult because this to-be repair position may be difficult for person or ground-based repair machine to reach. To reduce the risk of lives and the economy, can we use air robots to conduct inspection, rescue, or repair work after disaster? First, air robots can fly and avoid complex ground environment. Small-sized air robots can enter the small-sized environment to conduct inspection. Air robots can bring some tools to do repair or inspection, just like the group of air robots in this image. This image provides a vision for inspection and repair using air robots. Several small-sized yellow air robots fly into a destroyed house to do inspection work in a compelling way. Because the post-disaster ground environment is not suitable for air robots landing, one big-sided blue air robot can provide a large platform to carry, release, and guide the small-sized air robot to enter the small-sized environment. One large-sized blue air robot with its manipulator is doing construction crack repair work. In this way, air robots can help humans to do some high-risk work to avoid the risk of lives and economy in the post-disaster rescue activities. This image described both inspire me to do some research to provide proof of conception of post-disaster response activities using air robots. So it led to some research questions for me. The first research question is about how to implement an aero mountain environment cooperative for the inspection of the dark hole. The purpose is to find a solution to inspect the small dark hole using air robots and further prove the conception of post-disaster inspection using air robots. To answer this question, this led to two sub-questions. The first one is how to achieve stable flight of an aero carrier and its anchor a compelling UAV. The second one is how to achieve aero in-flight docking. The second research question is about how to conduct a construction crack autonomous repair using an aero system. The purpose is to find a solution to repair construction crack autonomously using an aero system to further prove the conception of post-disaster repair using aero robots. To answer these research questions, in our research, as shown in the left side, we explored mountain environment cooperative inspection solution using two different side aero robots, an aero robot, aero carrier, and a companion UAV to inspect the work of dark hole. The first step is the carrier carry the companion UAV to the inspection area, and then release the companion UAV and get it to the dark hole to inspect the inside. After its inspection work, it returned to the aero carrier using the in-flight docking method. Based on hardware and software of the mountain environment cooperative inspection solution, as shown in the right side, we reconfigured this aero robots. We combined a data manipulator and the aero platform to develop an aero system to repair the construction crack. The key steps including localizing the crack when it flies in the air, also short-range crack segmentation and repair operations. In order to provide a stable platform for cooperative inspection, we need to design an aero carrier and keep this aero carrier flight stable, especially during in-flight docking. We choose a cascaded flight control solution, a position control cascaded with a low-level attitude controller. In low-level control, we directly use the DJI-N3 autopilot. For the high-level control, we employed the model predictive control. As shown in the left side, we did a hover test in the lab, and the result is shown in the right side. The arrow is less than 9 centimeters in all directions. It indicates our aero carrier can hover stably to serve for in-flight docking. When aero carrier carry the companion UAV to a desired position or after in-flight docking, aero carrier need to anchor the companion UAV reliably. We design a docking platform including an aero anchor mechanism and a protection nets to avoid destroy the companion UAV and aero carrier when docking fails. As shown in the left side, we did the anchor test to test the locking successful range when the platform is shaking or wobbling. The marker yellowed feet was not anchored. More than 2 feet was grabbed to ensure its locking on aero carrier when aero carrier has large pitch and roll. To test the protection net's performance, the failure test was conducted, as shown in the right bottom. The results indicate if the docking arrow is less than 35 centimeters, the aero carrier and the companion UAV will be protected. To prepare for in-flight docking, the detection of the aero carrier is necessary. In order to find the aero carrier position and reduce the influence of the side effect of the cross aerodynamics between them, we redesigned a cross-shaped docking board as shown in the left side. Based on the marker detection method, we developed a docking platform detection method using visual arrow metric. Compared with only use feature marker detection, the minimum extend range was around 10 centimeters. This also benefits the companion UAV docking with more zoom. When the companion UAV is close to the aero carrier during its flight docking, they will be influenced with each other. For the small side companion UAV, we develop a height-dependent PID controller. In our experience, as shown in the right side, it can docking and anchor safely. During our experience, even the aero carrier move, the companion UAV still can follow its movement. Before chapter 5, all the work is preparation work to answer the question how to implement aero mountain environment cooperative inspection. We need to implement the full mountain environment cooperative inspection and to full answer this question. As shown in the left bottom, We modify the compelling UAV and add some sensors and a microcontroller to enable it to fly in a dark hole. In addition, to guide the compelling UAV to the hole interest, we need to know the position information of the compelling UAV and hole interest. We did a test about the compelling UAV and hole interest detection based on the colorful information and the depth information. I showed in the right side, it shows that in our data set, the hole interest detection precision can reach maximum 99.88%, and the compelling UAV detection precision can reach 100%. This means our detection method in our indoor environment is good and good enough. However, if in the outdoor environment, probably it will decrease. Based on the preparation work in chapter 3 and 4, the detection method of the compelling UAV and hole interest in this chapter, we conduct two main experiences, semi and full aero cooperative inspection experience. The difference between them is in flag docking. As shown in the left side, the semi-aero cooperative inspection was conducted. The air carrier can't land on the ground. And in the right side, the full one is conducted. The air carrier can't land on the ground. Implement to both of them are not just a simple method together. They are system work to finish a specific work. We need to consider computing, communication, payload, energy, software tooling, and test environment setup. To answer the second question, how to conduct the construction crack autonomous repair using an aero system, we reconfigured the aero platform of the aero carrier, combined a data manipulator to build the aero system to conduct the construction crack autonomous repair. We developed a data manipulator including extruder and an effector with camera and TF sensors. As shown in the top, we conduct the ground-based repair experience using the data manipulator. The means of failed error can reach 90.8%. As shown in the bottom, we also conduct 30 in-air crack 3D localization experience where the aero system is balanced above the crack in the air. The maximum average error in X, Y, and Z directions is 2.38 centimeter. Aero system reaching crack is an important step. As shown in the top, we also conducted 27 aero system reaching crack aero experience. The mean in the X and Y direction are both less than 13 centimeter. As shown in the bottom, when ultra-short range crack segmentation was finished, repair using a cement style material was fully conducted. The result was not perfect. The main reason for this is the data manipulator modeling error. We need to further consider more on the method of interaction between the manipulator operation and crack state. To conclude, in chapter 3, we answered the question how to achieve stable flight of an air carrier and its anchoring a compelling UAV by doing the flight hover test and anchor test. In chapter 4, we did the in-flight docking related experience and to answer how to achieve aero in-flight docking. With these two sub-questions answered, we did the full aero cooperative inspection in chapter 5 and to answer the question how to implement an aero multi-environment cooperative inspection. Finally, in chapter 6, we conduct a crack repair full procedure experience using aero system, and it answers the question how to conduct construction crack autonomous repair using an aero system. To conclude this thesis, we developed two software architecture for multi-environment cooperative inspection and construction crack autonomous repair, respectively. The control and the localization methods of both cases are the same. We both select the same MPC control and optimize based control localization. Our system architecture are not simply integrated all the methods. It leads to consider about computing resource deployment, energy consumption, system basic requirements, and communication. The most challenging is to build the test environment and tooling the system, and finally finish the specific works in practice. Our work is just proofs of conception of post-disaster rescue activities. It leads to be improved in robotics to implement in real-world post-disaster rescue. It leads to more further research. In the end, I would like to thank my supervisor, Dr. Rico Moko, and Professor Gita Witt, and all my supporters for your care in my PhD life. Thanks for listening. I'll give words back to you, Prorector.
So thank you very much for your clear presentation, and that will now lead us to the opposition and the questioning. Before going there, let me first welcome everyone on the live stream who's watching this presentation. And I was glad you already introduced your own supervisory team. Let me mention them once again, Dr. Muckel and Professor Weiss. They're not going to be asking questions according to Maastricht custom, but at least you know why they are in this session. Then my name is Ralph Peters. I'll be acting as today's pro-rector to guide you through this ceremony. Now then it's time for the questioning. And the opposition will now be opened by Professor Thuisman. Professor Thuisman was the chair of the assessment committee, and he's also acting as today's secretary to the degree committee. He also a chair in strategic optimization and data science at this university. Please, Professor Thuisman.
Dear candidates, as you've just told us, and as is also clearly demonstrated by the cover of your thesis, it's focusing on the use of cooperative drones for inspection and possible repair operations for buildings in disaster areas. The frequent appearance of news footage on disaster zones hit by, for example, earthquakes or acts of warfare clearly shows the urgent need for tools like yours. I'm therefore sure that you are addressing a socially high important topic in this thesis, and I would like to congratulate you and your supervisors on the work performed. However, while examining your thesis, I just kept wondering on how far we are from using tools like yours for inspection and repair operations in real-life cases. Your experiments clearly demonstrate a proof of concept for many of the tasks involved, yet the distance between the aerial carrier and its companion UAV appears to be rather limited in your experiments, and the size of the cracks on which you've experimented with autonomous repair operations is quite far from the cracks I see in news reports on television. I therefore wonder how many years it will still take to have tools like yours in full operation for the purposes mentioned. So I would like to ask you to enlighten the audience and me by reflecting on 1, the currently available travel ranges for the type of drones you are using without any recharging, and 2, how far the carrier and its companion can be apart from each other without significantly getting problems with their bilateral communication, which, as you mentioned, doesn't depend on any external antennas. As a third and fourth thing, like, what about the size of the cracks? So, I mean, how big type of drones would you need for realistic cracks? And how fast would any of this work be carried out? So this is the starting point. So the floor is yours.
Alex in Poland, thanks for your question. Actually, the question is really interesting, and also it's our it's kind of our future work we should consider. Before our research, we also consider these 3 questions. Actually, our experience and our proposal is kind of proof of the conception. And like you asked the question, why about it means our drone, our quadcopter, our aerobots, the power is limited, and we need to consider, we need to consider recharge problem. Also, for first question, I will ask you, For the small drone, just like in a cooperative way, for the small drone, if the big one, I mean the air carrier can carry more, if assumption carry more battery or power, it doesn't matter which kind of power, and it can transfer to electric power, we can add a recharger on the docking platform, and the small one can docking on the big one and then recharge it. This is the solution for the small one.
I understand, but can you just tell me something like how many meters or kilometers? And like I just want to know something about the size. Can you travel like many kilometers, or can you travel just tens of meters or hundreds of meters, or so? What's the scope?
Okay, in now the situation, I mean the technology development situation, and actually in the world, I mean the civilian drone, the maximum they can reach only like fly around the half an hour, and but how long? If you feel how far it is, I think like no more than 20 kilometers. Okay. So this is a limitation. This is our limiting. Yeah, actually, the question also we discussed with my supervisor before. It's really challenging for the drone. I mean the civilian drone. For other like the military, that's different question. And yeah.
Also, and what about the communication distance? Is that also like? I mean, the smaller drone probably has much smaller battery as well. So how far can the two be apart from each other?
In my thesis, the distance only 20 meters. So it's really, really limited. If you want the small drone want to explore the very long or very deep hole, or like the small space, it's really difficult. We actually I mentioned in my thesis, also said in the experience I made the issue, the Bluetooth was lost, and we lost the connection between the ground station and the Wi-Fi. Also lose the connection with the air carrier. So this is really, really challenging issue will lead to fix in the future actually. But this problem I already realized, and thanks your question. Actually, really, really good question. Actually, thanks.
Okay, and what about the cracks?
Sorry.
What about the size of the cracks? I mean, I think you need a very large, let's say, 3D printing device or something below your or.
Oh, you mean cracks or kilometers? Yes.
Yeah.
Oh, this one. Yeah, actually, relate. If only use the manipulator we use now, actually we only can repair very small crack. If you really want to use in real world application, actually now I think in the world no one did this, but if you really want to practice use it. I think the size of the not the data manipulator, probably others type of the manipulator, probably like I think I mean only the arm should be more than 1 or 2 meters, and the payload for the aeroplane also is really huge, because probably not use the battery, probably is like use oil like the car. It's like the like some Airbus, that kind of, it's different.
So the main
I will have to interrupt you, Professor Tasman, because time is already up. So I'm going to have to move to the next person in line. So thank you very much. And the opposition will now be continued by Professor Wienans, who was a member of the assessment committee, and he's a professor in machine reasoning here at Maastricht University. Please, Professor Wienans.
So, dear candidate, dear Yiyong, I have also read your thesis with much pleasure, but of course, I do still have some questions for you. One of the challenges you address in the thesis is so-called cooperative inspection. And you propose to combine a larger drone serving as a kind of model ship, which hosts and launches a smaller lightweight drone for inspecting narrow passages. And then I was getting all kind of these science fiction-like visions like Battlestar Galactica and Star Wars. And this makes me wonder whether there's a use case for a truly multi-agent approach, where you would launch several smaller drones simultaneously to perform the inspection. So I was wondering what your opinion here is. Is there a use case to make for such a system?
Highly extended opponent. Thanks for your question. Like you said, if you really want to use a swarm, because actually in our experience, we only use one compelling UAV and a carrier. It's kind of vision, just like I mentioned in the presentation. If we use a swarm drone to explore unknown
but wait a second, it's not a swarm. Yeah, it's basically we have one big drone that serves as a model ship and serves several smaller drones. So that is the system I'm proposing. So not a swarm of drones, but one drone that is hosting several drones.
Yes, yeah. I think this question should be considered about the communication, and if the big drone, yeah, because actually we didn't in this thesis we didn't consider about consider several different several small drone. We only consider use communication to communicate with one drone. This is, but if my peeling like this, if the drone should be further developed, our drone only can connect with the host.
Yeah, but assume that this you have enough docking stations and the platform is large enough. My question is also in how far scales your approach. So what's still missing? Can you launch simultaneously several drones? Could you dock several drones at the same time? Could you communicate with several drones? Or that's still a one-to-one relationship?
Yeah, I understand your question. Thanks. And if it was like you said, the several drone land at the same time, it's really challenging because the small drone between small drone they will cause a lot of wind. It's kind of wind, but it's kind of disturbance will influence others. For the this will pose really a lot of difficulties for the control and for the detection, because if the drone won't detect the docking platform, if another drone obstacle it, just block it, so it didn't know where it is. So I think if you want a docking, one should be one by one, not at the same time or at the same time. So first, they have the order. We should give the order of the system, and also the communication between drone and the companion UAV and the air carrier is really limited. Just like I mentioned before, it's only around 20 meters. So I think we should give the order, and also we should program in the companion UAV and give their it's kind of it's a rule. Thanks.
Okay. I still have a second question. I'm also looking to the prorector. Yes, it's still fine. Now on page 4, subsection 1.1, you discussed very briefly an alternative for aerial inspection in the multi-environment scenario, namely so-called morphing aerial robot. And then you refer to a paper from 2018.
Oh,
yeah.
2008.
Yes. It is on page 4. And frankly speaking, I was not convinced regarding the argumentation you use not to consider the alternatives, because you state in the first sentence of that section the payload of such an aerial robot is still limited, and thus its autonomy is constrained. So you mentioned a morphing robot as a kind of alternative, but you don't discuss any pros. And moreover, you cite a paper from 2018 here. So I was wondering what has happened in the meantime in the world of the morphing aerial robots. Could they maybe in the future be an alternative for your approach, a competitor? Because what I've understood is that this is a very interesting approach. So I would like your opinion here and an outlook.
Yeah, actually, during my master, I also do some. I did some research about morphing aircraft. The technology until now, I think the king. It's kind of challenging for the morphing aircraft is the control, because especially during morphing that moment, it's really challenging and will cause the aircraft to crash. So theoretically, I think the control is one problem. So we first to solve the morphing aircraft or drone the control problem. And if you want to use that kind of morphing aircraft drone into the disaster rescue, I think we should use not only one morphing aircraft. We should use morphing craft more than, more. It's kind of swarm, because if you only one, because just like the issue I mentioned, the control, if that failed, if that failed, no any other can continue to the rescue. And but actually morphing aircraft.
Wouldn't it be an idea to have your big mothership with a couple of regular drones, and then a couple of morphing robot ones for the really crazy inspection areas, a kind of hybrid solution? Isn't that the future?
Yeah, I'm gonna have you think about that because time is already up. I'm gonna move to the next question, so maybe for the later sessions. The opposition will be continued now by Professor Vos, who was a member of the assessment committee, and he's a professor in engineering science and robotics at the University of Luxembourg. Please, Professor Vos.
Yeah, many thanks. So first of all, I also enjoyed very much reading the thesis, and perhaps I'm also doing a lot of research, especially also with drones, and my background is mainly in control, and therefore I found some interesting questions related to that. So first of all, let's start with these, because you're using, I would say, two main approaches. One is MPC, and then you're using a lot of PID kind of control. Let's start with the MPC control. You use the MPC for the position control of the carrier. So my first question would be, okay, why have you chosen MPC for that control task? And especially with your application in mind, what would you say, what are the advantages, but what are also the disadvantages? What are the problems with MPC in your case?
Okay, highly extended Poland. Thanks for your question. The question, why I use the MPC control? Actually, before I use MPC control, I tried several different control, like the traditional PID control, like the geometric control, like the adaptive control, and finally we choose MPC control. The reason why I choose MPC control is first, from the theory, MPC control is based on the optimization. The disadvantage of it is just we need a lot, compared with the PID, compared with the geometric control, we need more computation resources. That's true. And why we choose MPC control? Because we compared with different like MPC geometric control, we fairly found the tracking arrow or like the hover stable, it's much better, the performance. So we choose MPC control. Yeah, advantage is just like after we test, we found based on our air carry, our platform, yeah, probably with different aircraft, different aerodynamics, probably different control, maybe in practice, I mean, in practice will be better. But in our experience, we tried a lot of experience. We found the MPC is better actually. Yeah, thanks.
Okay, yeah. Yeah, as the name already indicates, model predictive control uses models. Yeah. So, and then I was a bit checking in the thesis. I found then, and I was wondering. So first you developed these two linear models. Perhaps you know it was both in chapter 3 and chapter 4. You first had these. I think it was for the roll and for the pitch. There was first a linear first order model, and then you also derived a second order linear model. And then I was wondering, for what purpose have you used these models? And then I was also wondering, because in the different chapters, you had also different, the model structure was the same, but the parameters were different. So I was then wondering, okay, what has changed? Why have you this different set of parameters? Can you explain a bit? First, why these two models and why different parameters in the two chapters?
Okay, thanks for your question. For the MPC control, yeah, first we lead to the model. The model, it means inner side control model. So we lead to a response with the attitude control loop, and then we try to approximate the inner side model loop. So we built the first order model. Why we build the second order model? That's because we use the EKF estimator for the disturbance estimation of the system. Means, yeah, of course, just like our drone, the air carry and the companion UAV, the companion UAV can cause some influence to the air carry. It's kind of like the fan. They will give the wind to the big drone, but the wind is really weak or very small, but it will influence. So the EKF lead the second order model to predict the disturbance caused by the other drone or environment. That's why we like your second question, you asked why in each chapter the parameters are different. That's because in each chapter, actually in chapter 3, the configuration of the drone, the air carrier is different. It's lighter actually. It's lighter, because the board we didn't use cross board. We use just a square. So the weight is different. The dynamic is different. So the parameter is different. In chapter 3 and in chapter 4 and 5, they are the similar. They are the same almost, but also it's a little bit different. Because after the drone docking, they will carry the drone back home, back the takeoffing position. So the parameter also will be different. So because the drone in chapter 4 and chapter 5, I mean the companion UAV is different, also will influence the dynamics of full system. That's why the parameter is looks different, but actually method we use is the same.
Okay, good. Okay, good. Then I understand. And then I was wondering, okay, so you use the second order system then in the Kalman filter for the disturbance estimation. So that means for the MPC, you are using, at least I assume partially, the first order system, but then in addition, I think you still need another model part for the MPC, or that you did not mention, or?
Yeah, I mentioned just
very
like
quick
the first.
answer, please.
Just a first order. The first order is predict the dynamics of the inner loop control. So the inner loop control caused this kind of it's kind of predict. It's kind of because the MPC is predict the steps, the future steps. So that's why. The difference.
But then, in addition, I understand. Let's say you used this model for the closed inner loop, But then there's still a part, let's say the rest, so to speak, that you need in the MPC model. And what is this model about? Can you describe this? The missing part?
Optimization model, right?
Mm-hmm.
That is based on the MPC tools we just directly use. We just found from online, and we didn't develop optimization model. We directly use that kind of model to optimize our output, the control. We didn't develop the optimizing method.
Thank you.
Thank you.
We have to leave it to this. Thank you,
Thanks.
Professor Voos, for your questions. And the opposition will now move to Dr. Zhang. Dr. Zhang is an associate professor in AI for decision making. And she also was a member of the assessment committee, and she is affiliated with Eindhoven University of Technology. Please, Dr. Zhang.
Thanks. Dear candidates, first, I would also like to congratulate you on your thesis. You demonstrated a very broad knowledge from hardware, software to algorithms, and you connect them together and contributed to a very important application domain. So you have my compliments. While I was reading your thesis, I had some questions and comments I would like to discuss with you now. In chapter 5, you mentioned the two cooperative scenarios between the carrier and the companion UAV, semi-cooperative and also full cooperative. So often we see from the multi-agent or multi-robot study, the choice of how to collaborate between agents depends on multiple factors. For example, perception capability of each agent, computational power, and available resource for computation of different agents, but of course, the communication cost between agents. So my first question is, whether I'm correct that there's no direct communication between the aerial carrier and the companion UAV in your study, but you use a ground station as an intermediate agent for communication. And then the second question, I couldn't find the discussions, or I might miss it, on the complexity of different algorithms. For example, the whole entrance detection localization algorithm, and also the communication complexity between the different parties in your chapters. So do you have an idea on the computational and communication complexity of your study? And then on this line, my third question is, since you have the ground station as intermediate, in principle, you could run all algorithms in your ground station without any resource constraints and communicate back the necessary information to different UAVs. And then in principle, this two robots approach you used could be scaled to multiple UAVs. What do you think? Am I correct on this?
Extend Poland, thanks for your question. But actually for the first question, sorry, can you repeat the first question? Actually, I didn't remember it. The first.
Yeah,
question.
no worries. I will repeat. Is there direct communication between the aerial carrier and the companion UAV? As far as I understand, there's no direct communication, but you use a ground station as the agent.
Actually, for the first question, actually, they didn't have the communication between the aerial carrier and companion UAV because actually it's our communication message we based on the rules framework, and it's really the companion UAV we modified, not our developed. It's modified from DJI Tenno drone. That drone only can connection with the using the Wi-Fi with the ground station, because the Wi-Fi we used for the air carrier is connected with the ground station. So they can't, our drone, I mean the platform, the platform is really limited to connect with two different platform using Wi-Fi. This is because we didn't, but in our thesis, we mentioned the cooperative way is the cooperative way to achieve something, just like achieve enter the whole. I mean, the cooperative is the air carrier provides navigation information for the companion UAV. This is our cooperative.
Yeah, so I understand you have different tasks for aerial career and
Yes,
also the
yes.
companion one.
Yes.
Yeah,
yes.
that's fine. Yeah. Second question, the complexity.
For the second question, actually, during our experience and our research, we didn't consider about this. But if based on my understanding, if we will consider about this, I think it's really difficult based on the technology rate. I mean, the recent technology development, it's quite difficult. It's how to because the communication, the distance is really short, and also it's not so reliable sometimes. I mentioned before, like the Wi-Fi, we use not Wi-Fi, Bluetooth between the ground station. I mean the Wi-Fi connection between the ground station and a companion UAV. If you fly inside, sometimes it will lost. This caused the signal is really weak. So everything caused this issue, caused this kind of limitation is based on the limitation communication problem. So I think in my experience and the research, I think we can't solve this problem. But yeah, I think in the future probably they have some alternative method to change this kind of communication method, I think.
Okay, so I would like to directly ask you the complexity of the algorithm and this whole entrance localization algorithm. So do you have idea what's the computation complexity, meaning whether this is a polynomial time algorithm or is a linear or is exponential?
Yeah, actually, we didn't analyze the complex the algorithm. Actually, for the whole detection and the companion detection, actually, it's we just use the OpenCV library to detect it. It's really it not count too much computing, but for the crack detection, crack segmentation, it actually is use a lot of computation for our onboard like the drone. I mean the air carrier, the onboard computer is really limited. We tried, but it failed. It's because it actually needs some like GPU acceleration, accelerate. It's really difficult to implement. Only use the CPU and to calculate to segment the crack. Even we use a ground station, we only use one image. Actually, I think I have to mention this. Actually, no any influence for our experience. One image to calculate the crack because the crack is static compared with our takeoff position. So they won't change. So we only need one image and the position of that moment to that. I mean, the moment we take the image. So we can use the position and position stamps and the timestamps and the image to calculate the crack center position. So this is our solution, but no any influence for calculate the position of the crack. So
thank you.
That's my
We're gonna have to move on to the next member of the opposition. Thank you, Dr. Zhang, for your interesting questions. And the opposition will now be continued by Dr. Bonizzi. Dr. Bonizzi was a member of the assessment committee, and he is an associate professor in the area of signal processing and analysis here at Maastricht University. Please, Dr. Bonizzi.
Yeah, thank you. Dear Jon, also first congratulations from my side as well for your thesis. My first question is about the control component of your work. You used model-based approaches for control. At the same time, in recent years, a lot of work has been done in the direction of data-driven control, where basically you don't assume any specific model in advance. You kind of use the data to understand, to have an estimate of what could be a good model for a certain system, and eventually also find the optimal parameter values. I was wondering whether you consider also those approaches in your application, or if not, whether you could speculate whether they could be useful. Maybe they could make the system more efficient or more versatile to changing condition in an environment. Yeah.
Extend Poland, thanks for your question. Actually, really good question. Actually, we didn't try data-driven control solution. Based on my understanding and my knowledge, after leave from Maastricht and also study some in Maastricht, I think, yeah, like the data-driven, like the reinforcement learning control method, it's kind of future control solution, and also some groups in other universities tried this kind of control solution. Sometimes performs good, yeah, but most of them do this kind of research is in simulation environment. In practice world, in real world, it's really challenging, or it's really dangerous for the drone to do this kind of test. Yeah, first, based on my understanding, if I want to try use the like a reinforcement learning control method, I will combine the model-based one and the data-driven one. First, it just combine both of them and try to find the solution to combine both of them. If works, okay, not better, okay, that's okay, that's enough. And then we change it, fully use the reinforcement learning, and then just set up in the environment, in the simulation environment.
You're proposing kind of a hybrid approach, let's say.
Yes, I think it's really difficult to implement in real world. Yeah, because I only found one group use this one, but they didn't, success.
Okay, thanks. My second question is a bit different, still regarding, let's say, your model and the input to your model this time. So when a drone flies, or especially the carrier drone in your case, you assume that the assumption is that the drone doesn't know the environment where it's flying, so they have to map the environment. So they have to discover the environment while they're flying. Correct? Yeah.
Actually, they should know the environment, because we use the camera for the localization. Also, they did the environment, but not the need to map the environment. The map environment is for further research.
So my question is, assuming that, for example, your carrier drone is flying into a building after a post disaster, let's say, and assuming the building is partially collapsed, but not fully collapsed, right? So that's why you want the drone to go in the first place, because, for example, the building is still partially standing.
Yes.
Would it make sense to provide as additional information to your model the maps of the building, the original maps? And this could be used as a kind of a priori partial knowledge to help the drone to fly more quickly to the environment, or build maps more quickly and more efficiently, and eventually save time and energy at the end.
Yeah, actually, you said it's right. We can give there some information, just like a parallel information, not post information. Just actually now the development of the autonomous driving or autonomous flight, we can just build the map online, just directly on board. No need, you just put the drone in the unknown environment. It didn't fly before, and they can map the environment, and they know where they are, and then they fly from one point to another point without adding obstacle, without obstacle. So like you said, we need to give some information to the model. I actually have another solution. It's just like you said before, the data drive. We can use like the reinforcement learning. We can use that one first. We just use one camera. The image is our training input, and then we fly it manually, and give their command to the drone, and the drone try to fly based on the image, and then we training the network. We let the network learn how it fly only with the image. So this is the kind of solution. Actually, this kind of solution already achieved by other groups.
Yep.
This is
okay.
Yeah,
thanks.
yeah.
That's
Thank
enough.
you very much. Yeah, thank you, Dr. Bonici, for your questions. And then the opposition will be concluded by Dr. Poppa. Dr. Poppa is an assistant professor in computer vision at Maastricht University. Please.
Thank you for the introduction. Dear candidate, I'd also like to congratulate you for your work. I was also impressed by the number of subjects you investigated and the relevance of your work for the society. Saying that, I have a question about chapter 6, in which you are proposing a segmentation algorithm named SegNet. And I would like to ask you to comment on its relevancy today, given the real-time capabilities, but also in comparison to newer segmentation algorithms, like, for example, version 8. That will be the first part of the question. The second one is about the ablation study of the experiment you provided in section 6.5.1. You mentioned you selected 400 images from the METU campus buildings dataset, but I was wondering which is the variability of the texture of these buildings, whether that's enough for any scenario, or to which extent you can actually cover it.
Extend Poland. Thanks for your question.
No. Oh,
okay. Yeah. Sorry. Actually, I first ask the question. Thanks for your question. Actually, for the second question, I think also we need to improve. Actually, only in training, we only need 400 images, and we just use the enforced technology to get 1,200 images to train the network. Actually, the network already trained. It's pre-trained, so we just add this the correct image to train it again, and we test its work, because our purpose is to implement this knowledge. So we didn't do more on the training and the test. We found it can segment it in the air and also ultra short range to segment it. But the crack, you can in our thesis, we mentioned the crack is really limited, really small, and the background looks quite clean. And before actually we meet some issue, I think it is a segmentation network problem. Just like if you light on, and the foot of the drone, the shadow, they will detect it as a crack. This is the problem we need to further, I think, to solve. Actually, if in outside the sunshine and also will cause this kind of issue, but we only test indoor, and we only want to, the crack segmentation is really important, but in our full procedure of the repair is a part. So we emphasize the full procedure. We emphasize the full system is kind of proof. Yeah, actually, I fully agree with your appelling. Just the segmentation is not so enough for our demonstration. And also, like you said, I mentioned the data set only 400 images. Actually, we want to make more images, but the background, actually construction crack looks different from in real world, the construction crack is different from the crack in the lab. So we need to, I think it needs more time, but actually our time is limited in my experience, because we have to solve other problems, just like the drone, like the material, the extruder material, everything. We need to consider everything together, not only the segmentation. So actually, your suggestion is really good. I think we need to improve it. Thanks. Yeah, you can continue your second question.
Yes,
Sorry.
yes. Yeah, thank you very much. I also have some follow-ups about on some suggestions. For example, you could use transfer learning, or you can use data augmentation. But I definitely see that this is only a part of the whole system architecture. Yeah, so that was only a suggestion, that it's actually nice if you could also do an error analysis and then mention, well, like you said, with the shadows, but maybe with dust or with some other weather conditions.
I'll have to
In that
interrupt
case,
you. I think the beetle just signaled that it's time, but he's muted, so we didn't hear it. But he was clearly signaling Hora est. So I'm gonna end this. So, Yiyong Gou, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. And I request that you and your company await the results of our deliberations and our return into this live stream. So we will return, so please be patient. So let me check if we're all back. Yes, looks like we're all present, as far as I can see. Yiyong Gou. The degree committee here present online has assessed the quality of your thesis in your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Dr. Muckel is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Many thanks. Dear candidate, do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
Then by the authority vested in us by law and in conformity with the decision of the committee here present online, I hereby confer upon you, Yiyong Gou, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, you will soon receive the degree certificate signed by the rector, the secretary, and the supervisor, affixed with the official seal of the university, shown by the beadle. With that, many congratulations. As one of your supervisors, it's my honor actually to be the first to congratulate you. So, dear Yiyong Gou, dear Dr. Gou, together we are looking back now at a remarkable journey that led to this moment and the successful conclusion of your PhD project. I can still remember very well one of our first joint meetings at the robotics laboratory of the Department of Advanced Computing Sciences. And you probably remember at that time, actually, we were still, in fact, known as the Department of Data Science and Knowledge Engineering, where you presented a summary of your master thesis project. Since then, you have been growing your skills in a very remarkable way, and you became an essential member of the team. Starting as a, I would say, rather shy PhD student, constantly looked for instructions from your supervisors, you step by step developed into an independent researcher who is regularly integrating his own ideas to advance the project further. It was a great pleasure to observe this development during the many fruitful discussions we had together. What I like a lot about your work is your passion and dedication. With passion and dedication, you added many features to the drone, software and hardware frameworks that you found in our lab when you started your PhD project. Teamwork very quickly became a key success factor in your work. First of all, teamwork was essential in the way how you conducted research. And I believe, I think there was some point actually where you closely collaborated with almost all members of the lab in one way or another, because you integrated all these nice algorithm hardware into one project. Teamwork was also a key success factor in your work, since of course your very research actually is on the topic of heterogeneous drones that collaborate, so that one day we may actually see swarms of drones performing the challenges surveillance task we presented today. And I remember many meetings where we discussed how we best distribute the required artificial intelligence and software and control over the drones to ensure their reliable operation. It are indeed your team spirit, your passion and dedication that in the end made it possible that today I can congratulate you on your newly obtained PhD degree. What impressed me most during the last phase of your project was how consistently you worked also during the past 1.5 years, where you finalized your thesis report while already working on the next job. Having been in a very similar situation, finalizing my own PhD thesis while working on the next job, I can somehow relate to the immense pressure that you must have felt during this time and during the long times and to the long nights and little sleep that actually comes with such a situation. You have done that very well, keeping your positive spirit in all our meetings that for, very often actually for you actually were deep in the night. With all these efforts, I hope that the success is even sweeter for you. You told me that you are now working in China in a company testing autonomous cars. So I'm very happy to say that, like in your PhD, you stayed very true to yourself, still working with autonomous systems with the goal of keeping humans safe. And I'm sure that with all your passion and dedication that you showed in your PhD project, also in your new job, you will keep making significant contributions for that. So again, many sincere congratulations from my side. It has been an honor and a pleasure to be your PhD supervisor.
Dear Dr. Gou, also on behalf of Maastricht University, I congratulate you with the degree you have acquired, and I would like to extend my congratulations to your family and friends and your colleagues and everyone who has joined online. Thank you for being here today with us. And also a special thank you to all the committee members and those who put effort in preparing questions for today and discussing with you. So I hereby declare this ceremony for ended.